maybe have the similar variation as this 3, but this 3 is more closer to the true value, but this 3 may have some systematic error. So we see this data, have a higher precision, and this data have a higher accuracy. So from this small data set, you can see the difference between accuracy and precision. Accuracy basically is more closer to the true value, and also the variation is small. So the high precision is just that the variation is small. There may be some system errors. Okay, the randomization. I think the replication. Okay. Replication actually tell us, how repeatable our data is. So I think sometimes, we can even do some simple correlation analysis, to see how repeatable. So we do the correlation between the two replication. If the correlation is low, basically, the data is less repeatable, means there are a lot of errors. So, but there are more. If we have a replication, we can estimate the degree of freedom of error. We can estimate the error variance, and then we can do the the hypothesis test. So that's but it's a problem. How many replications should we have? Of course, at least 2. And sometimes should we have 3 or have more? Of course, the more replication have is more expensive. Some experiment maybe is not expensive, so you can have 3 replication or even 4. But some experiment, let's say in some animal experiment, even in the human pupil, we wanted to do some experiment about the damage, some car accident. That's very expensive. So, but in statistics, there are some theory to tell, if you tell me something, how big a difference we are going to identify by which power, we can give some idea about, the minimum population size you should use. The randomization is actually like a mess up. You mess up, the order of the treatment in the field. For the random sample, basically means, it's it's like you put some numbers in a black box. You mess them up, and then you random draw some from them. So that's a randomization. But in Excel, we can also do some randomization. So the randomization is important, because without that, basically we cannot do any estimation. We cannot do any inference. So, and also the sample cannot represent the whole population. So for the 3 principles, to me, maybe the randomization is the most important one. Because without that, we cannot do too much without the data we collect. Shall we take a break? So this design, actually there's no block control. So we call the completely randomization design. So which means, the 3 replication of one treatment, it can happen. It can be very close, in the field, because everything is random. So when we learn ANOVA, I think we should begin with a linear model. So for the ANOVA, actually, there's only one ANOVA, but there are a lot of different things. It's 1 factorial, 2 factorial with the interaction or without. So to really understand ANOVA, we should know the linear model. So for each ANOVA, if we can, make the linear model correct, so we can do the ANOVA correct. Of course, if the same data, basically you can use a different model. So there are different models you can choose. That's why we need to understand the essence of our data, to make sure we use the most suitable linear model, because different linear model, of course, give us different results. So in this design, if we take a look at the linear model on the right, we call the response, all the data we observed. So all the linear model have a constant curve, or sometimes we call the overall mean. And in this experiment, there only one factor is the treatment effect. So whether the treatment come from just one factor or two factors, it doesn't matter. Let's say in this design, we wanted to only wanted to compare, the different treatments, no matter what the treatments are. So in this model, these are the only effect we we wanted to investigate. But in addition, these are the effects that we are interested in. But there are something annoying is the error effect. So all the linear model, in addition to some effects, we can, we cannot get away of the error effect. Even in the physics, we can have a lot of, we have very good equipment, but the error, but it's just that the error is smaller. But in agriculture, in the field, so we have the error can be much larger. So the error effect sometimes also called residual, residual. In addition to the effect in the model, everything left, we call the residual effect. So this is the linear model with the complete randomization, randomized design, or abbreviated as CRD. So, for example, we have K factors, and each factor have L levels. So the treatment number is K multiplied by L. So this is our treatment number, and each treatment have n replications. So this will be the total plot required in the field. So in this design, this number of replication are totally randomly in the field. So as I said, the treatment, we can understand it as the combination between the factor and the levels of each factor. So there's also example, we have one factor with 4 levels and 3 replications. So in total, we wanted the experiment unit. This actually is the experiment unit is 12. So the arrangement, all the possible orders of the 12 treatment is quite large. So this is the combination number. So the randomization, which means just that one form this large number, so it can go like this in the field. So treatment 3 followed by 1, 4, and unfortunately the treatment 2, they come together. The 2 replication come together. But this it can happen. I said before, the randomly complete block design, so sometimes called the CRD or RCBD, anyway, there are different names, there are different order. So you can say that's a completely randomization block design or randomly complete block design. So which means that the randomization only happens which within each block. So it's not a a randomization across all the blocks. So when we see the linear model, so before we only have the treatment effect, but now the block actually become another factor. So in this design, actually, if we see the block as another factor, so the treatment actually is the major one. It's not really affected, but due to the design, so we can treat. So this analysis actually in sometimes when we do the ANOVA, you can take it as the two-factorial analysis without the interaction. So this is exactly this design, the model of this design. There's no interaction between block and the treatment. So the only effect are the other two this we call the two major effects. There's no interaction. So one is block, one is treatment, and the random error. So let's say we have 5 treatments, and we have 3 blocks. So this actually is not the order in the field. And when we do the analysis, we need to rearrange our data like this. And then once we have the data, we can calculate the mean for each treatment. So this actually we call the sample mean, can be used to estimate the true value of the 5 treatments. I think we talk about this. So in this design, actually we have the hypothesis to test. So which means there may be no difference at all, and alternative. So any statistical test have 2 hypotheses. One is called the non-hypothesis. Non-hypothesis is always more simple. So another one we call the alternative. So it's the opposite set of the non-hypothesis. So these are the 2 hypotheses we want to test. And the treatment, the design. So we have one factor, have 5 levels. The number of treatments is equal to 5. We have 3 blocks. So in total, we have 15 plots in the field. But there are 5 plots and each block. So the 2 words are too similar. Now it's block, plot. Don't get confused about it. So in the field, if we can find a large area for the 3 blocks, so it's okay. Actually, it's better because if we put the 3 blocks together, it's more convenient, to do the investigation. But that's not always the case. If we cannot find a big piece of land for all the replications, basically maybe we can find one piece of land which is uniform to have first the replication, and one here and another one there. So the variation between the blocks is allowed. So basically, actually, for this design, if there's no variation between blocks, so it's the efficiency will be same to the totally randomization. So it is the variation between the blocks, and then this method can have some additional gain. So if you do the experiment and after the analysis you find that the variation between blocks is significant, don't be shocked about that. So basically, that's exactly the reason you use the block control. If the variation between blocks is non-significant, as I said, whether you use the block control or not, it's more or less the same. Okay, so the 3 blocks, it can be, can go like this. how to do the randomization. So hopefully, later we can have we can still work on Excel. I'm not sure, how the system will be if we shift to Excel. In this course, actually, my idea is, every course we spend about 2 hours, on lecture, and 1 hour, to do some hands-on exercise. It's statistics. It's a calculation. It's not enough to just, I stand here, just talk. You sit there, just listen. And when the class is over, nothing happened. So I want we really can spend some time together, to work on some data. So in the, that hopefully that helpful for your, the graduate research. So in Excel, actually, there are a lot of functions available now. So we can easily, do the randomization in Excel, and also a lot of data analysis in Excel as well. So which you will see throughout this class. Okay. This also mentioned before, there are some other ways to minimize the variation. So we can use the block control to reduce the variation of errors. If there are some variation between blocks and we don't use the complete block design, so the variation between block will go to the error. So the error effect will be increased. So other consideration, is the field of operation. We should complete one block and then move to the other one. This also same, for the data collection. So it's better to finish one block and completely, and then move to another a different block. So these are some advantage. So can remove some set variation and increase the the experimental precision, and to and the statistical analysis, are also quite straightforward. So quickly, of course, there are some disadvantage. Maybe sometimes if we have some missing data, may have some trouble. The normal ANOVA actually we doesn't like the missing data. If there's some data missing, become unbalanced, a lot of good property associated with the ANOVA, does not occur. Then we need to use some mixed model methodology. Okay. So this course we don't touch mixed model. Okay. So there are some other design we will also introduce in detail in other class. So another one is Latin design, Latin square design. This design actually is the most accurate design, so which can control the soil variation in both directions, but also is the most expensive. So in this design, actually the number of replication is equal to the number of treatment. So because as you can see here, every treatment appear, if we have a treatment number 5, every treatment appear 5 times. So it's a square. So if the cost to grow one plot is expensive, this experiment is expensive. And when the number of treatment is large, we have a huge square. Sometimes we may be, it's not available. So this design, mostly, the number of treatment shouldn't be more than 10. And the incomplete block design. So let's say, each row is a block, but only have three plot. or 3 experiment units. So we have a Fab treatment. Of course, we each plot cannot have the whole replication, cannot have a Fab, but only have 3. So we can make Fab blocks, and also to have the 3 replications. This also we call it's a balance. It's an incomplete block, but it's a balanced design. So sometimes we can also use this design if the number of treatment is large than the number of experiment units in one block. Okay, so before there's some design to arrange to arrange all treatments. So sometimes we also wanted to cost. So other consideration is the field of operation. We should complete one block and then move to the other one. This also same for the data collection. So it's better to finish one block and completely, and then move to another different block. So these are some advantage. So can remove some set variation and increase the the experiment precision, and to and the statistical analysis are also quite straightforward. So quickly, of course there are some disadvantage. Maybe sometimes if we have some missing data, may have some trouble. The normal ANOVA actually we doesn't lack the missing data. If there's some data missing, become unbalanced, a lot of good property associated with the ANOVA, does not occur. Then we need to use some mixed model methodology. Okay, so this course we don't touch mixed model. Okay, so there are some other design we will also introduce in detail in other class. So another one is Latin design, Latin square design. This design actually is the most accurate design, so which can control the soil variation in both directions, but also is the most expensive. So in this design, actually the number of replication is equal to the number of treatment. So because as you can see here, every treatment appear, if we have a treatment number 5, every treatment appear 5 times. So it's a square. So if the cost to grow one plot is expensive, this experiment is expensive. And when the number of treatment is large, we have a huge square. Sometimes we may be, it's not available. So this design, mostly, the number of treatment shouldn't be more than 10. And the incomplete block design. So let's say each row is a block, but only have three plot or 3 experiment units. So we have a Fab treatment. Of course, each plot cannot have the whole replication, cannot have a Fab, but only have 3. So we can make Fab blocks, and also to have the 3 replications. This also we call it's a balance. It's an incomplete block, but it's a balanced design. So sometimes we can also use this design if the number of treatment is large than the number of experiment units in one block. Okay, so before there's some design to arrange the to arrange all treatments. So sometimes we also wanted to compare. We have two factors. Which factor is more important or have more variation? Is there any interaction between the two factors? So we have another design we call the factorial design. So the basic idea, if one factor have 3 levels, another factor have 5 levels, so we can put them together. We can do the experiment for all 15 treatments. So that's the factorial design. But this design, if we have more factors or more levels, the number of treatments can be huge. So there are some other design, to reduce the number of treatments. So one is the splat plot. I say, we have, one plot as the planting date, and all the these other, all the mutations. So there's a one factor one called the major, major plot, and factor B as the subplot. And the alpha design, each block, like a square, so the material are randomly arranged, in the 3 replications. So this design actually is quite often used in breeding, especially for the first year of yield trial. The breeders may have thousands of genotypes to test. So this design, is quite useful in that situation. And in genetics and breeding, we have the multi-environment trial. So we have a number of genotype growing in a number of years and a number of locations. So basically, we have to consider the location and the year by environment. So that's another special experiment in genetics that allow us to study the genotype by environment interaction. So sometimes the interaction, this we call the non-crossover. This is called the crossover interaction, which means one genotype is better than other one in one environment, but it's worse than another one in another environment. So this happens in genetic study. Again, it's the example, for the 5 wheat varieties. We can grow it in 2 environments, and each environment will have 3 replications, and these are the data we collected. And from this data, we can conduct the ANOVA for each environment. But of course, we can also conduct the ANOVA, across the 2 environments, and estimate, the genotype by environment interaction. So the variables, in reality, the variable, which means the summation can have different value. So the value is not fixed. So constant is, is summation we can fix, like the planting date. So for the data we record, the sum data maybe is a constant, but the many times we have the variables. The variables can have 2 classifications. The one is the quantitative, which like the flower color, and the ounce of weight. It's just it's a qualitative. We can many times we have the quantitative, like a planting head, But we need to be know the quantitative doesn't mean always continuous. We also have some data like a number of green or Taylor number. It cannot have any decimal point. But those kind of data many times also called quantitative. It's not like a flower color, white or red. You may terminology in genetics. So the traits investigated in Mendel's experiment, actually they are all qualitative. So it's the green shape, whether it's round or wrinkled, color, and the the position of the flowers and the plant head, is whether it's tall or short. This trait actually we don't need to use any equipment. It can be measured by by our eyes. So these are the qualitative traits. Quantitative is like this. If we measure the human height in one population and in a big sample, so we can also make the groups for the data, but it's hard to see which one is short, who are short or who are tall. So it's a continuous distribution. So this is always goes with the quantitative traits. So basically, there are another kind of traits in genetics. We call the threshold traits, like the disease. Of course, you can either have the disease or don't have the disease. It looks like a qualitative, but behind the trait, there are threshold value. If your blood pressure is above a given level, the doctor will say, "Oh, you have some problem." There are some range, So if we concern the blood pressure, so then that disease can become a quantitative trait. Some variable can be independent. So independent, which means this variable can have a different value, but we can control. Let's say the treatment, we can select 5 variety or 10 variety. So that's something we can control. We can have 3 levels of fertilizer. We can have 3 planting date. So the planting date is also a variable, but we can fix that. So those variable we call the independent. So the dependent, which means we can say that's a response, the response to the independent variables, like the final green yield, and the different planting date will give us a different yield, different fertilizer, amount of fertilizer will also give us a different yield. So mostly the traits, phenotypic traits we observed or we recorded, we call the dependent variables. And sometimes we have a one dependent variable, but sometimes we can have multiple. If we have multiple independent variables, we can study the major effect from each variable. So here the variable can be understand effect, but we can also look at the interaction. So whether there's a very special combination between planting date and the fertilizer, can give us the highest yield, something like that. Of course, when we consider multiple factors, we that will result a large number of treatments, and also the design can be very large. the independence of the data. So the data we collect is like, because this can be met by the randomization. So the independence of the data, let's say, basically means it's the observed data from different replications. They should be independent. Without the independent, as I said before, we cannot do too much on the analysis. So mostly we assume, basically, when we do most of the analysis, we assume the observed data, they are independent. If they are not, it will be very hard. Interaction, which means sometimes let's say if there's no interaction. If there's no interaction, so we have two factors. So if this level for this factor give us the highest yield, and for another factor we have another level give us the highest yield. If there's no interaction, so we put the two levels together, will give us the best yield. So that's the case when there's no interaction. So the best combination can be worked out from the best level for each factor. So if there is some interaction, so basically, the best level for this factor, the best level for other factor, if you put them together, it doesn't mean, it doesn't have to be, have the best output. So that's the interaction. So in that case, basically it doesn't make too much sense to talk about, what's the best level for this factor, what's the best level for other factor. We must consider, the two factors together, and then we can talk about what the best combination. So this, I think this happens, why we in the ANOVA analysis, we need to consider, whether there are some interaction between two different factors. Many times for the factor design, basically we want to identify the best combination, which give us the best yield, which give us the best response. So we need to know, whether there are some interactions or not. And then, we can identify the best combination. Okay, so that's the some like some introduction to the principle of design and some designs that we are going to touch during this course. So for detail, so this is the today. And the next three classes will, review some basic theory on probability and statistics. Because without that, it's very hard to talk about the design only. So we hope everyone takes some introduction courses on probability and statistics or biometrics. If you never take any classes in statistics, well, maybe you are still okay with this course, but you need to spend maybe more time. So we spend from the class 5 to 9, we talk about some design in detail with the analysis. And another 2 classes talk about some fitness test and some regression. And the last few classes, I wanted to introduce some genetic data analysis. So how many students in this class have the major in corpus science? Anyway, probably for corpus science, you may do have some genetic data. So we want to, in this course, give you some ideas, how to do some analysis of some genetic data. It's still, the statistic method is we apply the statistics to genetic data. And we only for most contents we only use Excel. So this class is not about SAS or SPSS. We don't even use that. We use Excel. I think if there are probably 90% of statistical analysis nowadays can be done in Excel. And the genetic data analysis we develop in our group, we develop some software, because this analysis we don't have any method available in Excel, so we have a special software for to analyze your market data, to build the genetic linkage map, to find identify some important genes. So the next we will work on some exercises here. So the basic idea is, let's say we have two parents. We collect some data on plant head. So this plant head, form the same parent, but form different individual plants. Of course, every data is different. So the variation here actually reflects the error effect in the field, because it's like the uniformity trail. Everything is the same. The genotype is the same. The management is the same. So the variation only is the random error. So this is the first two parents, and F1. If we make a cross between the two parents, we have an F1 hybrid. So if the two parents they are homozygous, so F1 is also it's heterogeneous but only have one genotype. So all the individuals have the same genotype. So the variation here is also reflected the random error. But the F2 there may be some genetic difference between the two parents. So for these individuals, each individual have a unique genotype. So the variation we observed here actually include both. There are some genetic variation and random error. So the next we are going to find out what's the mean, what's the variance in each population. And if the first three population only have one genotype, so the variation can be used to estimate the error variance. So from this variance, we take away the error variance, then that's the genetic variance. So the variation here can be, separated into two components. This also ANOVA, So the total variance can be separated into two parts. So all the ANOVA actually in the end we can separate the whole variation between the variation from factor A, variation from factor B, variation from interaction, and the variation from the random error. So this also the ANOVA, and through that we find the genetic variation in this population, and then we can find the heritability. So that's then it's become the genetic data analysis. Okay, that's this one. And the next we want to see to some distributions. So in Excel there are functions for different distribution in statistics. So if we wanted to see if the two parents, basically this is the estimate from the first three populations. So the number here you see that's the estimation of mean and the estimation of the error variance. So if I wanted to see how the phenotype looks like, so that's the distribution. And the first three population we assume is a normal distribution because we only have the error effect. So error effect is normally distributed. So that's also one very important condition in statistics. If you don't believe the error is normally distributed, there's no statistics. And then if we assume, there's a one gene, basically the F2 population is a mixture population of the three. And these are the proportion of the three, components. And I want to see how the F2 phenotype in F2 looks like. So then we draw a mixture distribution. Do you have any idea to have this graph in Excel? Okay, if you don't know this exactly, I will show you. If you already know that, we don't need to do this such exercise. But I think at least one or two of them know that. You never use any statistical distribution in Excel or regression, ANOVA. You estimate the population mean. Mean of a number of values, never. Well, then what do you do in Excel?
Currently, most of those analysis students use other software like Horizon, Achieve.
Well, you are rich.
Excel is more complicated.
Really?
Excel is more simple.
So every day you use the SPSS rather than Excel?
Like for regression, I think softwares like Minitab, Origin, those softwares are easier.
We'll see. Because of every computer probably have the Excel. Not every computer have a SAS. So if you only do ANOVA regression, I don't suggest you to spend $10,000 of money, to buy software. I think the reason is just you don't know the Excel have such a strong functionality. So if you know, you. Okay, so now let's see. So we will continue. Okay, so let's see how if I can shift to the Excel here.